So here we go on Lesson B, Gravity and Orbits for Unit 3, Circular Motion and Gravitation. For this lesson, we are focused on standard number 4, gravity. Students will understand that gravity is a universal attractive force by which all objects with mass attract one another. They will understand that physical principles behind the orbits of the planets and satellites. And here will be our learning targets for this lesson. So one of Isaac Newton's greatest claims to fame is his explanation of how planets orbit the sun. In order to explain orbiting planets, let's imagine first something like a cannon like this. So we fire a cannon, the projectile flies through the air and lands some distance away. So now let's imagine we fire our projectile at a greater initial velocity. We're going to get a greater range, but we're still going to end up hitting the ground. In both cases, our projectile follows a curved path because it's being accelerated downwards by the force of gravity. And the greater the velocity of the projectile, the farther it's going to go before it strikes the earth. Newton showed, however, that if the velocity is great enough, the curving path of the projectile will have the same curvature as the surface of the earth. Now, he explained this by imagining a mountain on the earth that was so high that its summit was outside the earth's atmosphere. On top of that mountain was a really powerful cannon which fires a projectile horizontally. The projectile follows a curved path and still eventually hits the earth's surface. But now say we add more gunpowder to the charge and fire another cannonball. So now we have a greater initial horizontal velocity. This cannonball is going to travel a greater distance before it too will hit the surface of the earth. And if we continue to do that and give it a greater and greater initial velocity, eventually the velocity is great enough so that the curved path of the projectile matches the curved surface of the earth, and the cannonball never gets closer to the surface. It keeps falling forever. The most important point of this qualitative analysis is that in the absence of air resistance, an orbiting projectile is in free fall. Now this is kind of a strange idea, but it's worth careful thought. An orbiting projectile is really no different than a thrown baseball or a car driving off a cliff. The only force acting on it is gravity, but its tangential velocity is so great that the curvature of its trajectory matches the curvature of the earth. When this happens, this projectile falls under the influence of gravity, but it never gets any closer to the surface, which curves away from underneath it. So when we first started talking about free fall, we said that free fall acceleration is always directed downward. Now what we see then is that free fall acceleration is actually directed toward the center of the earth. Okay, so if we look at a projectile falling down to the ground, we say that it is under the force of gravity, which acts downward. But if we zoom out a little bit into this, we find that force of gravity is really directed toward the center of the earth. And so for any projectile in orbit, this projectile is just moving around the earth. The direction of the force of gravity changes as well as the direction of motion. Now, as we talked about in the last lesson, a constant force that always points toward the center of a circle causes the centripetal acceleration of uniform circular motion. Now, because for a thing that is orbiting, the only force acting on that orbiting projectile is gravity, is the force of gravity, and we're assuming that the projectile is very near the surface of the earth, we can say that acceleration is equal to the net force over the mass. That net force is brought about because of the weight of the object. Weight is mg, and we end up with g. So this is where we get acceleration due to gravity. And we know that since this thing is an orbit, it's moving in a circular path, we know that that's a centripetal acceleration, which is equal to v squared over r. Therefore, if an object moves parallel to the surface of Earth with the speed equal to the square root of rg, then the free fall acceleration provides exactly the centripetal acceleration needed for a circular orbit of this radius. So an object with any other speed will not follow a circular orbit. We can see then that this is exactly the same as the critical velocity we talked about in the last lesson. Now, with Earth's radius being about 6.37 times 10 to the 6 meters, we can use this to find that the orbital speed of a projectile just skimming the Earth of a smooth, airless Earth is right around 7,900 meters per second, or 18,000 miles per hour. So we can use this to calculate then the period of that satellite's orbit. The period, remember, is the time it takes for one revolution. So for this Earth-skimming, airless planet Earth projectile, we end up with a period of about 84.4 minutes, or 5,065 seconds. And of course we get this from the previous lesson where we talked about orbital speed. Now, of course, this orbit is unrealistic. Even if there were no trees and mountains, a real projectile moving at this speed would burn up from the friction of air resistance. Suppose, however, we launched the projectile from a tower of a height of, say, 200 miles, which is well above Earth's atmosphere, which, by the way, is about the height of most low Earth orbit satellites. If we were to apply that radius then to this, we'd end up with a period of about 87 minutes. And when we did have space shuttles, they would orbit at an altitude of about 200 miles in about 91 minutes. So that's a pretty decent calculation there. It's not great, it's not perfect, but it's pretty good. So when we talked about weightlessness before, we saw that it occurs during free fall. And we asked the question whether astronauts and their spacecraft are in free fall. And now we can answer that yes, they are indeed in free fall. They're falling continuously around the Earth under the influence of only gravitational force, but never getting closer to the ground because Earth's surface curves beneath them. So weightlessness in space is no different than the weightlessness of a free-falling elevator. So weightlessness does not occur from an absence of weight or an absence of gravity. Instead, an astronaut, a spacecraft, and everything in it are weightless because they're all falling together. It's really their apparent weight is zero. So if a satellite is simply falling around the Earth with the gravitational force causing a centripetal acceleration, then what about the moon? Is the moon obeying the same laws of physics, or do these celestial objects obey laws that we can't discover by experiments here on Earth? So applying what we've just looked at, taking into account the moon's radius of 3.84 times 10 to the 8 meters, we would find that the period of the moon would be about 11 hours. Well, this is clearly wrong. The period of the moon's orbit is about a month. So Newton believed that the laws of motion that he discovered were universal and should apply to the motion of the moon as well as to the motion of objects just around him. But why should we assume that the free fall acceleration is the same at the distance of the moon as it is near the Earth's surface? If gravity is the force of the Earth pulling on an object, then it seems reasonable that the size of that force, and therefore the acceleration because of that force, should diminish with increasing distance from the Earth. Which is exactly what we find happening. We have something that's further away from the surface of the Earth pulls on it less, and we have a lower acceleration due to gravity. And like the distance from Earth to the moon, it's about 60 Earth radiuses away. So as we can see from this, that is very, very low amount of g there. So that would account then for this difference in what we calculate versus what we experience. Newton proposed the idea then that Earth's force of gravity decreases with the square of the distance from the Earth, which is the basis of Newton's law of gravity, which we will discuss right now. So Newton is credited with the discovery of gravity, but of course he didn't really discover it. People knew gravity was there. What Newton did that was so revolutionary was he described gravity. He gave it a description and was able to explain its effects far from the Earth's surface, out into space, and explain the behavior of planets, and to formulate mathematical law that accurately described the force of gravity between objects with mass. Really, the greatest success of his theory of gravity was to successfully explain the motion of planets and moons and other objects in the sky. A pretty popular image of Newton thinking about this idea of gravity after an apple fell on his head, which, is an amusing story. But even Newton himself said that this notion of gravitation came to him as he was sitting under a tree and saw an apple fall to the ground, and it occurred to him that Perhaps the apple was attracted to the center of the Earth, but was prevented from getting there by the Earth's surface. And if the apple was attracted, why not the moon? And so Newton's genius was taking this sudden realization and extending it to explain that the force of the Earth on the moon was identical to the force of the Earth on the apple. So in other words, gravitation is a universal force between all objects in the universe. It's not so big a deal, it's not real shocking today, but nobody before Newton had even thought that this motion of objects on Earth had any connection at all with the motion of the planets around the sun. So more so than his laws of motion even was this universal law of gravitation that really rocketed him into his famous status that he has now. So Newton's theory was really very simple, that gravity is a force of attraction between any two objects that have mass. So two objects sitting on a desktop attract each other with a force that we call gravity. They don't go flying together because gravity is a very weak force. It's only significant when one or the other of the masses is really enormous, planet-type size. And that's why we don't feel gravity, we don't feel that attraction to objects as we go about our daily activities. So Newton's law of universal gravitation says this right here. The force of gravity is equal to G times M1 times M2 over R squared, where F is the force of the gravity, M1 and M2 are the masses, R is the distance between masses, and G, this G is something called the universal gravitational constant. It's different than lowercase g, acceleration due to gravity. That is not what this is. This G is instead what we call the universal gravitational constant, and it is equal to 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. And the value of G is the same everywhere in the universe. It's a universal constant. Now, Newton's law of universal gravitation is something that we call an inverse square law. Now, this means that the force of gravity gets smaller or larger by the square of the distance between the masses. The force is directly proportional to the product of the masses, so if the mass of one of the object doubles, the force of gravity would double. But if instead the distance is doubled, the force of gravity would decrease by a factor of 4. And this is because it decreases by the square of the distance. So inverse square laws are really common in physics, and we'll see a couple more before the end of the year. It's also really important to understand, too, that the force of gravity between two masses, those forces are an action-reaction pair. And some other important particulars of the law of universal gravitation are that gravitational force is a field force between two particles in all mediums. Force varies as the inverse square of the distance. Force is proportional to the mass of the objects. The gravity force acts from the center of the two objects. And the gravitational force is always attractive, and it cannot be shielded or canceled. We can't block gravitational force. So applying this theory to an example here, we have a girl, Brandy, 42.5 kilograms, sits 1.5 meters from a boy, George, who's 63 kilograms. We want to find the force of gravity between them. This tell us how attracted they are to each other. So the information that we have, we know these things. We apply that to the universal law of gravitation. We end up with 7.94 times 10 to the negative 8 newtons. This is a really small amount of force. So we can see that the force of gravity is a really weak force, especially when we compare it later on to some of the other fundamental forces. So let's take a look at gravity on other worlds, and we're going to use the moon as our example. Suppose we take an object to the moon and we want to find its weight on the moon. There's kind of two perspectives that we can use to look at the weight of this object on the moon. We can look at first the little g perspective, and then we can look at the big G perspective. So let's look first at this little g perspective, where we'll use the same expression for the weight of that object on the moon as we do on Earth, or weight equals mg, where this time, however, the g has to be the g of the acceleration due to gravity on the moon, which is 1.62 meters per second squared. So for the little g, if we want to find the weight on the moon, we just simply use weight equals mg. Under the big G perspective, we would use Newton's universal law of gravitation, where we say that the force of the moon on that mass is equal to g times the mass of the moon times the mass that we're trying to find, divided by the square of the radius of the moon. We'd use the radius of the moon. If that mass is on the surface of the moon, then we're using the radius of the moon as the distance between the center of mass of the moon and the center of mass of that object. Now what this is telling us is that this force, the weight of the object on the moon in the little g perspective, and the force of the moon on the mass, which we find in the big G perspective, are equal. So what we can do is equate these two forces like this, where we now end up with a single expression. And we take a look at this, we find that the mass of the object, our object sitting on the surface of the moon, ends up canceling, and we have a single expression for the free fall acceleration on the surface of a planet, where that g of that planet, the acceleration due to gravity of that planet, is equal to universal gravitational constant times the mass of the planet over the square of the radius of the planet. Okay, so now we're going to combine some of the things that we've been learning here to discover how we can find the orbital velocity and orbital period of an object in a circular orbit. First, with orbital velocity, we're going to assume that the orbit of a satellite around the Earth or any other massive body is a circle. Most orbits are not circles, but instead are ellipses, which was discovered by Johann Kepler in the 1600s. But we're going to keep it simple and look at a circular orbit. So in order to have a circular path, a centripetal force is required. This centripetal force is supplied by the force of gravity between the two bodies. So we can set the centripetal force equal to Newton's universal law of gravitation, and we end up with this right here, where we have the centripetal force here, we have Newton's universal law of gravitation here. We end up with v squared equals big G times m1 over r. So we end up with an expression for orbital velocity, v equals square root of gm over r. Now it's important to realize here that the mass in this equation is the mass of the object being orbited. Okay, so if we're talking about a satellite around the Earth, this m would be the mass of the Earth. It's the mass of the object being orbited. So now let's think about the orbital period. Orbital, of course, period is the time for one revolution. And for an object in uniform circular motion, velocity of it is constant. Okay, so that's v equals x over t. We solve that for time, it's x over v. Okay? Of course, this distance being traveled out by this whatever object it is, say it's the moon around the Earth, is equal to the circumference of that circle. Now, of course, this v is still, it's the orbital velocity that we just derived, which is a square root of gm over r, and we insert that into our expression here, we end up with this. So when we square both sides and then clean the whole thing up using our wonderful algebra skills, we end up with this. In a continual cleaning of it, we end up with an expression for orbital period. And again, it's important to remember that the mass in this is the mass of the object being orbited. So in other words, this is telling us that the square of the period of the orbit is proportional to the cube of the radius of the orbit. So to end, we have a question. If the mass of the moon were doubled, but it stayed in its present orbit, how would its orbital period change? Pause the video for a moment, think about this before continuing and seeing the answer. Well, we know from our expression for orbital period that the orbital period is in here. There it is. Orbital period depends on the mass of the object being orbited. So if the moon were to be doubled in its mass, it would not affect its period, its orbital period at all, because it's the mass here is the mass of the Earth, the object being orbited. So the correct answer here would be C. The period would stay the same. Okay, so that'll end this lesson on gravity and orbits, and we will see you in class.